Okay, so welcome back in this course Advanced Manufacturing and Process Modeling. So till the last class we have discussed about homogeneous nucleation. So today we will start with heterogeneous nucleation. So in heterogeneous nucleation, as I told earlier, that in case of heterogeneous nucleation, the chances of nucleation are more in the preferential sites that are provided within the liquid melt, unlike homogeneous nucleation where the probability is same everywhere. So for example, you can see in this slide, it is you can see that there is a nucleation event of a product particle beta is shown over the a foreign inclusion delta within a liquid melt of alpha. Okay. So, then the product particle which is nucleated over delta, so it is basically making a angle between the base substrate and the front liquid solidifying front. So, then that angle is basically theta. So, to calculate the nucleation kinetics, we assume that the surface tension forces at point O. So, we need to balance the surface tension forces at this origin point. So, then so how we can do that? So, at this so then we can also calculate the delta G heterogeneous, that is the free energy change due to heterogeneous nucleation by balance of surface tension forces. So, here this is the product particle beta. So, volumetric free energy change is basically V beta into delta G. V beta is the volume of the particle plus gamma alpha beta. Alpha beta is the surface area of this face. So, this is the alpha beta surface. Surface energy gamma alpha beta and surface area alpha A alpha beta plus this surface area. So, that is the beta gamma. So, that means the A beta gamma into surface energy gamma beta gamma. So, then because of the nucleation of the product particle beta, so then this is the nucleation that alpha gamma interface, that is the inclusion particle delta and the liquid melt alpha. So, that free energy need to be deducted from this to get the balance of the surface tension forces. So, so here it is minus gamma alpha delta into the surface area, that is this is the beta A beta delta. So, that is what is giving you the delta G heterogeneous, that is the free energy change for heterogeneous nucleation. So, now if we skip a few steps, we can show that delta G C heterogeneous, that means critical free energy change for heterogeneous nucleation is equal to 16 pi gamma alpha beta cube by 3 delta G square into 2 minus 3 cos theta plus cos cube theta by 4. So, so this term is basically that one what we derived earlier in case of homogeneous nucleation. So, that means delta G C heterogeneous is equal to delta G C homogeneous into this this is the function of theta f theta. So, that is referred here as f theta. So, now it is based on the weightability of the product particle. So, that means when the product particle makes only point contact, that is with the foreign inclusion or even the mold wall. So, then cos theta is equal to cos 180 degree is equal to minus 1. So, then if you put the value of minus 1 here, so then we can see it becomes 2 minus 3 plus 1. So, that means it becomes 0. So, then sorry. So, if we put the value of minus 1 over here, then it becomes 2 plus 3 and minus 1. So, then it is becoming as delta G C heterogeneous, delta G critical heterogeneous becomes delta G critical homogeneous. So, that means so there is basically when it is making only the point contact. So, then basically it is only the making the point contact the product particle. So, there is no benefit out of heterogeneous nucleation is achieved. So, that means it is basically as similar as homogeneous nucleation. That means there is no change in the nucleation barrier, but when the particle completely wets the foreign surface, that means here if the particle is wettability like this, it is wetting the whole surface. So, then cos theta is equal to cos 0 degree, and again if which is equal to 1. If we put the value of 1 over here, then we get 2 minus 3 plus 1, that is 0. So, that means delta G heterogeneous critical is equal to 0. That means virtually there is no barrier for nucleation, which is a impossible kind of event, but theoretically it is possible. So, that means there is no nucleation barrier at all. So, I mean what we see in reality is basically a compromise between this case, that means delta Gc is equal to delta Gc homogeneous, and this case, that is delta Gc heterogeneous is equal to 0. What is the usual case then? So, for hemispherical shape of the contact of the nucleated solid, so then the included angle is basically 90 degree. So, then cos 90 is equal to 0. So, if we put the value of 0 over here, so we can get basically delta Gc heterogeneous is basically equal to half of delta Gc homogeneous. So, so this is the case which is most we are trying to achieve. So, how we can achieve? We can basically promote heterogeneous nucleation within the solidifying melt. So, by incorporating some external seed particles or such, for example, grain refiner or modifying agents within the solidifying melt, so that they can facilitate decreasing the nucleation barrier, and we can get basically a lesser nucleation barrier and higher nucleation of primary grain, primary solid within the liquid melt. So, for example, for aluminum alloys, it is the aluminum 5 titanium 1 boron, which is used as a master alloy, which is used as a grain refiner. And also there is strontium, aluminum strontium is used as a modifier. So, they have the role of decreasing the this nucleation barrier, so that we can achieve a higher nucleation of primary grain. So, this is a just example problem, so that you can it becomes easy for you to understand. So, for example, if you are asked to calculate delta Gc heterogeneous as a fraction of delta Gc homogeneous when the interface have the following energy, that is gamma alpha beta is equal to 0.5 joule per meter square, gamma alpha delta is equal to 0.5 joule per meter square, and gamma beta delta is equal to 0.01 joule per meter square. So, from surface tension equilibrium, we can say that cos theta is equal to gamma alpha delta minus gamma beta delta by gamma alpha beta. So, then we can determine the value of cos theta as 0.098. As we have seen earlier, that if when the particle completely wets the foreign surface, that means cos theta is becoming equal to 1, the value of cos theta become equal to 1, then virtually there is no barrier for nucleation. Here this value of cos theta is very close to 1, which is 0.98. So, hence we can calculate the value of delta Gc heterogeneous, and here we basically can calculate the delta Gc heterogeneous as 0.0003 delta Gc homogeneous. So, the nucleation barrier virtually disappears due to the very low energy of the interface between beta and delta. So, we should always target towards achieving this. So, in that way we can basically decrease the nucleation barrier, and we can achieve very fine grain microstructure, and also that in turn will provide much improved mechanical properties. And also there are many other physical properties of the solidified object which can be impacted due to the fine grain microstructure that we can achieve within the solidified objects. So, with this now I will introduce the concept of nucleation rate and growth rate. So, please recall that earlier I have told that so the solidification driving force is basically the undercooling, that is the lesser as the temperature drops from the equilibrium fusion temperature Tf. So, you can see here, so this is the equilibrium melting or the fusion temperature Te. So, as we are going down from here, so delta T value is increasing. So, at a certain delta T value, you can see that we are getting the maxima of the growth rate of the already nucleated product particles, nucleated embryos or nucleants, whatever. And as we know that as we are going, I mean getting higher delta T, I mean values, we are getting higher nucleation rate. So, we are getting maxima of growth rate somewhere here. So, I am terming it as T g, and we are getting the maxima of nucleation rate I somewhere here. So, I am terming it as T I. So, you can see that delta T value at T delta T value for delta T I is much higher than delta T g. So, this is so the nucleation, I mean undercooling requirement to achieve maxima in the nucleation rate is higher than the undercooling requirement for achieving maxima of the growth rate, and the transformation rate, that is dx dt, which is a function of both growth rate and nucleation rate. So, maxima of that we are getting at a intermediate delta g, I am so terming it as delta t x. So, the so if we write here, so we can see that, so delta t nucleation maxima greater than delta t transformation maxima greater than delta t growth rate maxima. So, this is the relation that is prevails in all the metals and solidifying alloys during solidification. So, so this is basically just to show you that how the growth rate initially it is slow due to very few nuclei, the transformation rate x with time, then in between it increases, and again towards the end of solidification the transformation rate which is a function of both nucleation and growth becomes slow, because there is not enough space available because of the impinging individual grains, and so that is why again the transformation rate becomes slower. So, it is slower at the end, it is slower at the beginning, and it is exponentially growing in the intermediate timeline. So, with this we are we have finished the basics of the solidification mechanisms. So, now we will discuss about the 10 rules for good castings. So now we will discuss about the engineering part of it. We have discussed about the solidification science of it. So, now the engineering part of it, what are the engineering thumb rules? The number 1 is you have to start with a good quality melt. Number 2, avoid turbulent entrainment of the surface film in the liquid. Rule 3, avoid laminar entrainment of the surface film on the liquid. Rule 4, avoid bubble entrainment. Rule 5, avoid core blows. Rule 6, avoid shrinkage. Rule 7, avoid convection. Rule 8, reduce segregation, and Rule 9, reduce residual stress, and Rule 10 and the final rule is provide location points. So, before going ahead, I would like to tell you that although these are the thumb rules that are necessary to achieve good castings, but it is not possible to completely eliminate, say, laminar entrainment or turbulent entrainment or convection. It is impossible to completely eliminate them, but our effort should be directed towards achieving minima and maxima of certain conditions, so that we can get the optimum set of properties that are both physical as well as mechanical in the solidified objects. So, that is the goal. And so now we will start with the first rule, that is start with a good quality melt. So, you can see this is a particular example what is shown over here, that is if you do not start with a good quality melt, if there are a lot of inclusions, then what can end up get a generation of lot of blowholes in the part post solidification. So, that is why it is recommended that you start with a good quality melt. How you can achieve that? You can do the melt preparation within the inert atmosphere or under vacuum environment, and also post melt preparation you can basically do proper degassing, and number 3 is you can do proper slag removal. So, these are one of the 3 practices that you can follow, so that you can prepare a good quality melt, so that you can end up getting a cast part with sound structural integrity. Okay. So, number 2, rule 2 is the so avoid laminar entrainment of the surface film. So, what is that? So, it generally happens due to downhole pouring after gravity, under gravity. So, horizontal transfer into the mold uphill counter gravity casting, where melt fills the mold in an uphill mode. Counter gravity process, of course, is thought to be ideal, which abides by all these 10 rules that we are going to discuss one by one. So, the maximum velocity requirement. So, almost for all the liquid metals, critical velocity is close to 0.5 meter per second. So, this velocity requirement can be explained from the Reynolds number. I mean, so that is, some of you might have already studied it in some of your undergraduate or postgraduate days. So, I mean, so this will be basically the, I mean, rho Vd by mu, Reynolds number. So, so rho is the density of the melt, and V is the velocity, D is the diameter if it is flowing through a circular section, or the characteristic length if it is flowing through a flat section, and by divided by the dynamic viscosity. So, this value should be and adjusted in such a manner, so that the velocity, if it is around 0.5 meter per second, then the Reynolds number will be in the laminar regime. And then, I mean if it goes beyond that, then certainly the melt will enter into the turbulent regime, and in the turbulent regime there is every possibility of the, I mean that we will just discuss next. There is chances of gas absorption, bubble damage, and also there is a chance of, I mean, entrainment of surface film within the solidifying melt. So, if liquid exceeds that, then its surface film may be folded into the bulk of the liquid, which causes a variety of entrainment defects. Hence, the no fall requirement. So, the spruce would be designed to have a cross section just large enough to take the required flow rate to fill the casting in the target fill time. So, it should not be like the sprue cross section. So, as we have discussed earlier about the sprue of the, I mean, so this is basically the sprue. So, the sprue cross section should be large enough so that it flows full, and if it should not be more than what is required to flow full by the liquid melt. In that case, I mean, it will cause, I mean, gas absorption, and also it can cause the entrainment of surface film. Okay. So, then avoid laminar entrainment of the surface film. So, it is not that if the flow of the liquid melt within the mold cavity is in laminar, I mean, in laminar regime, then there cannot be surface film entrainment is not possible. I mean, that danger still is there, and when it is possible if the melt pouring becomes intermittent. And so, if because of some intermittent pouring, arrest of the forward motion of the meniscus happens. So, this is what the example is shown over here. So, then facilitates the formation of thick surface film, because it is solidifying metal. Mostly we are dealing with metals with having significant thermal conductivity, which tries to cool fast, and that is why the chances of surface film formation because of the solidification of the liquid solid, I mean, liquid solid front is very high, and then the new metal rolls over a new fresh oxide. So, assume that there is a stop while pouring the liquid melt within the die cavity. Basically, we are pouring from here, then suddenly it experiences cooling and there is a surface film formation, and again the fresh metal comes in, it rolls over it, and then this portion which is solidified, it gets entrapped within the solidified object, and that creates the, I mean, entrainment of the surface film. And in the so this is the example of arrest of the forward motion of the meniscus. And the next case, water flow, the oxide flow tube. So, despite high velocity of the flowing metal, so you can see this is the case of water flow, and during that entrainment of the surface film. I mean, so it is like a waterfall flow of the liquid melt from this I mean, entry point to this cavity. So, then although the velocity is very high in the radial direction, so but transverse to this, I mean, perpendicular to this direction of the flow, the velocity is basically 0. So, a oxide tube, if it forms at the top of it, then it may not, I mean, it may not be possible to be detected, and also that can very well form and it can get trapped. So, what it can result in, once this I mean, rectangular object gets solidified, there can be a tube like defect, and the metal gets solidified over that, it can get trapped within that. So, that can cause a, so that is an example of laminar entrainment of the surface film, because of the waterfall flow. So, this is an example. So, the precipitation on an oxide flow tube. So, this is a thick oxide, this is the air gap, and this is the thin oxide. So, this kind of defects, the moment there is mechanical loading on the solidified metallic specimen or the composite object, then these defect regions will trigger crack initiation, and which can cause failure, catastrophic failure to the object, or it can significantly decrease its service life, and also it decreases its capability, its fracture toughness and ductility. So, this is the the reason and the possibilities of the impact of the laminar entrainment of the surface film. So, then rule 4, so that is to avoid bubble damage. So, sometimes folding action of the oxidized liquid surface contains small pockets of accidentally enfolded air, that is trapped bubble. So, bubble can be originated from different regions. Please recall that in the previous classes I have discussed about the casting several sub sections of a mold cavity. So, that time we have discussed about when we have discussed about the sand mold, we have also discussed about cores. And so, during melt pouring within the mold cavity. So, there are some like we are using some binders or additives within the sand to for bind it, and also we are using the binders additives in the core. So, that can undergo evaporation because of the heat imparted by the liquid melt. So, and that can cause gas evolution, and also there is a chances of hydrogen absorption in case if we are talking about liquid melt of aluminum alloys or light metals. So, then those can cause bubble can entrap as bubble within the solidified object, and if a single bubble is does not remain as such, even then it can because always there is a tendency because of the buoyancy force from the liquid melt, a bubble originated say from a core placed over here. So, then that bubble will try to escape by its travel towards the free surface of the melt, and then it will be vented out to the atmosphere, but while it journey to the free surface, it gets disintegrated into multiple bubbles, and some of those bubbles they get trapped within the solidifying melt, that means within the mushy zone, and do not end up reaching the top. Maybe the bigger of that can reach at the top and get burst, but some the smaller disintegrated bubbles, so they get trapped and they cause bubble trail, and that is a dangerous situation for a cast object, because that significantly decreases the mechanical property and the structural integrity of the cast part, and moreover it also degrades the physical properties, for example thermal conductivity and also the density significantly. So, the passage of a single bubble through an oxidizable melt is likely to result in the creation of a bubble trail. So, even though the main bubble may be lost by bursting at the liquid, that is what I have drawn here and tried to explain to you, the trail remains as permanent damage. So, the bubble damage is usually a mixture, the residue of bubbles and bubble trails. It is a typical entrainment mess. So, in some stainless steels the above phenomena is observed, that is mixture of bubbles and cracks. Okay. So, now the rule number 5, that is to avoid core blows. So, the pressure of gas in the cores may rise to a level higher than that in the liquid, and that results in originating blowhole. So, a bubble smaller than 5 mm dia can split the oxide film and gets trapped. So, that is a case of trapping of the oxide skin, of trapping of the bubble is shown over here. So, then a detachment of the bubble of a bubble from the top surface of a core, bequeathing a bubble trail as a permanent legacy of its journey. So, core blows from most easily from upward pointing feature. So, it is quite similar with the previous case, that is the avoidance of bubble damage. In this case the bubble can be originated from the absorption of hydrogen or the other gaseous evolution of the gases within the melt, and in this case specifically is the source of the gas, I mean source of bubble formation is basically the cores that are used kept within the cast object to make hollow sections. For example, this is the casting and this is there is a hollow section that needs to be created within the object. So, that is why we use cores within the cavity, and these cores are basically developed by a different grade of sand, but that are basically bound with the additives, and those additives faces evaporation at the onset of liquid melt when it is exposed to the liquid melt within the mold cavity, and then they can cause this bubble formation, and these bubbles can get trapped within the solidifying mush, and they can generate this bubble trail later on. So, so this is rule 5, and now we end up to rule 6, avoid shrinkage. So, shrinkage is a phenomena that we have discussed also earlier in the class. So, it is basically happens due to the density change between the liquid and solid state of matter. So, as we know that with solid, like for example, aluminum alloy, it is liquid state, its density is around 2495 gram per cc, and in the solid state its density is around 2700 gram per cc. So, aluminum liquid and aluminum solid. So, because of this density change, there is a shrinkage that is experienced by the solidifying object, and that shrinkage is called solidification shrinkage. Apart from that, there are other two shrinkages, which is because of the decrease of temperature of the liquid melt, which is called liquid shrinkage, and the other one is the solid shrinkage, which happens due to the decrease of temperature of the solidifying object post solidification. So, basically the most dangerous and critical shrinkage which is responsible for defect generation within the cast objects is the solidification shrinkage. So, the solidification shrinkage can be mitigated effectively by positioning risers. So, risers can be open or blind based on their requirement. We will of course discuss about riser design in subsequent classes. So, appropriate design and positioning of the riser can alleviate this defect of so shrinkage can be avoided by that. So, after this we will move to the rule 7, which is avoid convection. So, again this is better said than done. So, it is very difficult to completely eliminate convection, because this basically happens due to the natural convection within the solidifying mold cavity, because of several contours present within the solidifying cavity, and because it is more common in case of alloys with a solute component, significant solute component involved. So, it which triggers thermosolutal convection, and what we can do is basically we can effectively design the dies so that we can feed the mold cavity in such a manner, so that it can be helpful to reduce segregation, and thereby it can be helpful to avoid convection and convection driven defect generation within the solidifying object. So, it is more related to the related to the flow physics that we observe within the mold cavity, and which can be effectively dealt with. It can be dealt with by effective design of the riser, ingate, and also the runner dimension. So, we will of course discuss about in the within this module itself in subsequent classes about how we can basically design a mold cavity effectively, so that we can achieve proper flow physics within the mold cavity, so that in turn we can get desired mechanical properties in the solidified object. So, thermal convection in case of bottom feeding, this is an example, and then near elimination of thermal convection by top feeding. So, this is the most stable one. So, so these are some examples how we can basically avoid convection related defect formation within the mold cavity. So, this is another example of avoid convection is shown. This is a single crystal turbine blade. So, this is generally made of nickel based superalloy, So, investment casting often provides numerous convective loops in works assemblies. A typical works assembly for the casting of nickel based turbine blade is shown over here. So, this is the works assembly which is shown here for investment casting, directional solidification of turbine blades. The grain structure of the etched blade reveals the flow path where the original chill grains remelted in patches. So, you can see the effect of remelting of the original chill grains over here and over here. So, the narrow section of the trailing edge and the thick bottom right is not penetrated. So, these are the locations where you can see that the microstructure is different than the other locations. This is basically, these are the left out portions where this remelting phenomena is not possible. So, these are the regions which is not penetrated by the convective loops of the liquid melt, which are otherwise responsible for remelting the initial microstructure, and that is why it is basically happening due to the compositional inhomogeneity, and also which is basically originated due to the thermosolutal convection within the solidifying cavity. So, we can what we can do over here, we can design the die in such a manner so that there is minimum backflow and there is preferential flow and there is no so reverse flow. If we can eliminate, then we can also eliminate the damage, the compositional differences originates due to convection. So, so now we will go to the rule 8. So, this is called segregation. So, micro segregation between dendrite arms is a consequence of normal freezing of an alloy, and macro segregation it's a global phenomena that we observe within the cast object on the which is irreversible. So, it threatens to scrap the casting if the composition is outside of the specification limits. So, heavy steel castings funnels low density solutes mainly high in carbon into the feeder head of the casting. So, that is quite natural. So, because riser is the also called the feeder head. So, that is the last solidifying location of the casting and it should be like that. So, this is a case of positive segregation, since this is the last solidifying portion of the solidifying mold geometry. So, there the segregation becomes higher, micro segregation, but the macro segregation which is more dangerous. That means the composition of the solute element should be homogeneously distributed within the cast part. That can be achieved by appropriate process control and design of the cavity. So, there are several factors at play, and that is also a basic fundamental reason of the essence of this course, where we are also going to discuss in depth about process modeling, which can be useful to achieve the desired set of design and design attributes in terms of process, in terms of the component, in terms of the die cavity, in case of casting or in case of other processes, so that we can alleviate these kind of defects. Okay. So, so then rule number 9 is basically reduce residual stress. So, in practice the stress remaining in the casting is usually assessed by scribing two lines on the central bar and accurately measuring their spacing. The bar of length L is then cut between the lines, and usually the cut ends spring apart after the cut completed. So, after machining away one part of the cast surface, so this is what is talked about here, and the strain is therefore delta L by L. Delta L is the dimensional change divided by the original length, that gives the strain, and the stress sigma can be found assuming the Young modulus E. So, as we know, stress varies the strain. So, stress is equal to Young modulus into the epsilon, that is the strain. So, basically we can get the value of Young modulus by getting stress divided by strain. So, main cause of the development of residual stress is that the different members of the casting cooling at different rates. So, we will also discuss about how we can design the different subsections of the cast part effectively, so that we can reduce this effect, although we cannot completely eliminate this, but we can significantly reduce the problem of having different cross sectional attributes at different locations within the cast object, cast part, and that which results in differential cooling rate at different sections. And the residual stress primarily originates because of the in the regions where there is a drastic change in flow path cross section because of the intended change in the dimensional attributes of the solidified object. So, here the strain generated is basically I mean delta L by L is equal to alpha delta T is equal to residual when. So, then the residual stress becomes equal to, as we know that stress is equal to Young modulus into strain. So, that means alpha delta T into E. So, this is how we can calculate the residual stress value. And then so I mean so these are the 10 rules that we have discussed. And after this we will enter into the different casting processes, and we will also learn about the geometric attributes, how we can control the flow physics in case of the mold cavity, so that we can get the parts with sufficient structural integrity. That those things we will be discussing in the subsequent classes of this module. For now we are finishing over here for today's class. So, see you in the next class. Bye.